Thank you, everyone. So hi, my name is Andrew Ho. I'm a product manager for the machine learning infrastructure team at Airbnb. I'm joined by, is your mic on? No. I'm joined by Nikhil Simha, who's a software engineer also on the machine learning infrastructure team. So today we're here to talk to you a little bit about Zipline, what it is, what it's trying to solve. And in a short summary, Zipline is Airbnb's machine learning data management framework. It's a little bit of a lofty title. It can mean quite a lot of things, so hopefully we'll clarify that during this talk. So the first part that always comes up is really identifying the entire user workflow. And so this is a little bit about the origin story of Zipline, what it's here to solve. And so one of the initial things that we are looking for is what is the workflow that we're targeting? And when you really think about that for data scientists, it comes down to feature engineering. And it starts off with an idea. And the idea is the data scientist thinks about new features, different problems they want to solve, and they come up with some hypotheses, right? And then the next step usually is data discovery. I'm sure you have this within your teams and organizations as well. You have a great idea, you want to do something, but is the data actually there? Does the organization save it properly? Is the raw data in some form or another actually within the company and usable? Next is building your training set. And so taking that raw data, cleaning it, taking out null values. And then it really comes down to training and evaluation, right? And so you actually train on it. Does it actually work out? Are you getting the precision and accuracy you're looking for? If it's not panning out, do you iterate this on again? Do you go back to the idea stage? And we see this cyclic behavior where data scientists are able to reiterate and look for new solutions, as well as what's the secondary step to that, right? And this is what the talk is really kind of focusing on. It's productionizing it, which is a whole different beast in workflow. And we'll talk a little bit about that soon afterwards. So Airbnb Zipline is just one component to Airbnb's machine learning infrastructure. Airbnb Zipline is primarily focused on these two components of the data scientist workflow, which is data discovery as well as the training set, building out the training set. So with this data discovery, there's a couple of questions that really need to be solved. And this is the mindset we had with building out Zipline. It's really thinking about what the problems are and how do we build out a machine learning infrastructure that can simplify this for data scientists, as well as when bringing it into production, simplify for machine learning engineers. So the first question that always comes up is where is it, right? Where is the data stored? What does your organization or what do you use to store your data? Is it within Hive tables? Do you use event logs? Do you have raw database dumps? And so really figuring out where your data is one of the crucial parts, important steps into doing this. Next is it good? Is it of high quality? Is it reliable that you can use? And this is really a data quality check. Third, will it continue to be good? As many of you guys have known, when you build out a model and continuously train on data, what's the guarantee that the data source doesn't change, right? How is it being calculated? How is it being stored? What kind of contracts do you have with the upstream dependencies? And so that's a key thing that we do focus on. And this is both technical as well as organizational, right? So you do need to go to the other teams or whoever is managing that input data, as well as ask them, will it continue to be good? Can you commit to this contract so that I can take a strong dependency on it? And lastly, this is actually a key thing for us is, has it already been done before? So Airbnb, I think it has 3,500 employees now. And so you find that a lot of different teams are working on similar problems, or there's a lot of shared knowledge that can go around. And so how do we build a common infrastructure that can share this knowledge across the teams, share this across Airbnb so we don't have this kind of incidental complexity, which is essentially duplicating work, rebuilding things over and over again, and that's just wasted effort from us. Next, it's the training set. So a couple questions come up with the training set. The first one that comes to mind is what processing engine to use, right? If it's a small data set that you have locally, you can just run a simple Python script. If your data is quite large and you need a distributed processing, then you can actually use Spark. And so there's the idea of what processing engine to use and what really works for the scale you're working with, as well as the different requirements for latency. And I'm sure if anybody here works at a large corporation, there's also COGS involved, right? Costs. And so that's another thing to think about. Next, backfilling. And so another key thing with the training set is thinking about backfilling. No one really wants to recompute all their data over and over again. That's a lot of compute power that's wasted, that's a lot of time that's wasted. And so we do focus a lot on backfilling to make sure that if you do add a new feature, we can just backfill that feature rather than having to recompute everything. And this is a key one that I think a lot of people are focused here. It's point-in-time correct windows. How many people here, I'm sure quite a few, have had the issue where they have joining two data from different data sources, and it turns out one data is further along in time than the other. And if you don't have this point-in-time correct windows, then the thing that is further along in correctness and has more signals can actually predict more accurately, but it will fail, well, it won't do as well in production. And so we do want to make sure that we have these point-in-time correct windows so we can scope all the features in different incoming data within the same scope of time. So going into production, you have your training set generation. This is the training set that's been generated by Zipline. And then it goes into model training. This is kind of a separate service that we have within Big Head, and we'll talk a little bit more about in the next talk, which is push the model into the prediction service, the online features part. What kind of online features do you need? As well as if you have an online feature that you want to plug it back in to score the data again or trade the data again, how does that work out? Model monitoring, this is really important as well. Going into production means that you're trying to create a model that's lasting for the long term, and so how do you model its health? How do you monitor its health? How do you monitor its stability? How do you monitor its availability? How do you make sure that you have constant checks on this? And with that, in a similar category, it's data quality monitoring, right? So how do I make sure that the data quality is still the same and nothing's changing upstream? How do I have my own checks and guarantees to make sure that whatever is happening upstream with the input source, that things are remaining constant rather than changing on how they're calculating things? And so the core of the presentation is, what is Zipline? I'm sure everyone's dying to know. It's a part of Big Head, which is Airbnb's end-to-end machine learning platform. As I mentioned before, it does focus on that data discovery and training sets part. And so training sets is a key component that we want to focus on, as well as a feature store. And so one of the key things for the feature store that we are really focusing on is feature sharing, right? And so at Airbnb, we're really looking to share all the knowledge and different features with other teams. And so we're looking to build this kind of collaborative infrastructure tool where it makes it easy to expose different features to other teams so that they can leverage all the work that's already been done to clean the data and all that. And then data quality, right? How do we make it as simple as possible for people to figure out whether the data is clean? How do we continuously have these checks? So a week, a month, a year down the line, people can check some kind of dashboard to see what the health of their incoming data is like. So some of the concepts that we will focus on is the data source, just where the data is coming from, the input source, the feature set. So after getting that raw data, after kind of data munging that raw data, what is the feature set like? How is it stored? How is it shared? The training set, the set that you've chosen to use for training your model. And then finally, a client, right? And we have a client, a Java-based client that can be used to fetch all the features. And so within the feature set, I'm sure people are curious about where is this data actually coming for, specifically for Airbnb. Specifically, they are within Hive tables, event streams, and mutation streams. Within there, we leverage pretty heavily the primary keys. The primary keys are particularly useful because we do a lot of the joins on it. And so when you have different streams of data, I'm sure many people do have that, doing these complex joins across different streams, you need a good way to have a good property to actually group by as well as do the joins on. And then the timestamp, like I mentioned before, point-in-time correctness is one of the key things we focused on fixing for this within Zipline. And so we do have a precise timestamp that's always passed along to make sure that we can scope things to the proper windows. So the feature set, it can come from multiple sources. I did talk about backfills. That's one of the things that we do want to focus on as well. How do we backfill features? How do we make sure that we don't waste computing power to recompute a lot of the features that are already there? And this is actually a pretty interesting thing that Zipline does that I think I've seen pretty unique within the industry, which is essentially data migrations happen. You migrate from one database to another. This happens everywhere. It's just because it's really hard to predict what the technology is going to be in a year's time, 2 years' time. And so one cool thing that Zipline does is it can actually take in from multiple sources while you're doing migrations and kind of stream along both sources. And so you have this continuous stream of data. And this is really nice, especially for all of those database migrations that always tend to happen. And so this is a key way to make this a really durable infrastructure so that you don't have this hard dependency on one specific data source. And as it migrates along, you can actually cling on to both of them. So because I was talking a little bit about the abstract, here's an example. So you can see right at the top, we have the owner, and then we have a source. And it's just a Hive query, and so you can see that the type is Hive. And then for the bottom, we actually have the features and bookings, and the doc is just a little bit of a comment and string that we add onto it to describe what we're actually doing. The operation is listed as sum. Just do this. And the window is actually that time slicing of window. That's a key component to really think about. I think the best way I've heard it from our team was that it's almost like a time-traveling infrastructure because how much we're focused on this time slicing and windowing, especially for all the feature management. And so it's a very, very cool infrastructure for that. And data quality, this is actually just a GIF of our UI for it. And so you can see that we have a couple things over here. We have a correlation analysis. We have a clustering analysis as well. And then we expose two different things, which is the first part right there is essentially the distribution of the data. So how do I get a glimpse of the data at a glance to make sure that I'm taking the right dependencies? And then the second one, it's actually listed out in table format, so you can dive into a little bit deeper, as well as see the values inside there. Awesome. And I'll switch over this part to Nikhil.
I apologize for the yellow tint. I think it's because Flux is turned on my laptop. Let me quickly switch it off. Should be better. Sorry about that. All right, so now you have your features ready, clean, you know what it looks like, and you want to create your training set and create a model, right? So basically, you don't always create the feature sets. You pick out what are the features you need from a data exploration UI, and you see what are the keys that you want to create your training set for. So you write a driver query, which basically gives what are the keys and what are the timestamps at which you want to create these features, right? And Zipline takes care of computing these features based on the timestamps in your driver query and make sure they are all point in time correct. Right. Let's look at an example of the training set query. Right. If you notice here, the user provides, so this is a very simplified example. Typical training sets have hundreds of features from different feature sets. So in this thing, you see there are three feature sets in play, three features in play. There is a simple query which gives the primary key, which is the user, and the timestamp for which you want to create the training set for. And you also provide other things like dependencies, what's the team, what's the name of this model, what is the start date for this training set, et cetera. Right? This is how it actually kind of looks like. The first three columns are what's produced by the training set. So it provides what the primary keys are, and Zipline automatically figures out where to pull the feature sets and how to join them with point-in-time correctness. Right. So let's talk about backfills. Let's say you have this new feature set idea, and you want to add a couple new features, right? You don't want to like discard your old training set that you computed. You want to like efficiently reuse what you have there, right? So training sets don't really look like a green rectangular blob. So a bit more explanation here. The x-axis is the feature columns, and the y-axis is the time. And you want to compute new features for more time. So you need to like fill this L shape to create the new training set, right? And we have noticed that backfilling is a major bottleneck when you're iterating on your training set idea, right? So efficiently computing new training sets is a huge deal for speeding up your data scientist workflow. So next, we need to talk about label offsets. So you don't always have the label at the same time as you do prediction. Let's say you're trying to predict stock value of a particular stock in the next week. You need to offset your labels data by a week, right? And Zipline takes care of this with just a parameter. You can configure what the label offset is, and you get the point-in-time correct training sets, right? Now, let's say you have this golden training sets, you trained your model, it's all looking good, and the performance is great. You want to make sure that your model has access to all these features when it's scoring online, right? And there are a bunch of challenges when you want to recreate these features for online scoring. Again, backfills, it's a large theme. You want to make sure that all the backfills for new features is really efficient. You don't want to cause a lot of downtime when you backfill. You want to make sure for things like fraud detection and for search ranking, right? You want to capture user intent really quickly, and latency becomes really important. So most warehouses are designed with daily snapshots in mind. Data lands at the end of the day, some computation happens, and resulting table lands at the end of the day. But how do you get from there to real-time features in your feature store, right? And mutations. So mutations are important because let's say you depend on a raw database like MySQL, right? And you don't depend on a Hive table. How do you make sure that you do real-time queries on top of this data? One thing is you can query your database directly with huge aggregations, right, which will never finish in time. So other thing is to change the database transactions into streams and publish them and create features off of that. Right, we will also see how Zipline does batch correction to handle mutations. Right. Quick overview of how we architect this whole thing. We use Spark to compute the batch side of the features, and we use Flink to do the streaming part. I will explain in the next slide why we use Flink instead of Spark. I think it ties back to the continuous processing talk. This is what the architecture looks like. User writes a conf, and we produce the batch snapshots. We continuously stream the DB mutations or the event streams into the key value store. And the Zipline client does the aggregation finally and publishes it to the user application. So if you see, the aggregation is split across batch, streaming, and the client. Right? So there is a bunch of right-side aggregation and read-side aggregation happening in the system. And if you notice, the batch snapshot is updated daily. So your state exists in Zipline only for a day, which has a side benefit, which is GDPR compliant. You can refresh the store easily. Not many people talk about GDPR, but it's a pretty hard thing to bake into your systems. So I'll address the streaming question now. Why are we using Flink instead of something like Spark? Streaming, so this image is taken from Spark blog for continuous processing. So it describes why micro batches lower bounds or create a lower bound on your latency that is at a second scale. For fraud applications, you need to be at least in the millisecond scale of latency because fraud is automated. It happens in a matter of milliseconds, and micro batches don't really work there, right? With the new continuous processing model in Spark, this is still experimental. We would switch over to this when this becomes a bit more stable. You don't have to deal with the second scale latency because events are processed as they come in. But there is a trade-off here. The previous model allows you to do exactly once processing, right? I'm guessing we will talk more about this in the continuous processing talk, but here you will lose that exactly once guarantee, but you'll get less latency, so it's a trade-off that you can make through Zipline. Right, and let's get back to how we are going to aggregate the values across batch, streaming, and the client. Right, we need to compute fixed length sliding windows, right? And the window size can be as large as an year or as small as 5 minutes, right? So to efficiently do this, you need to keep a certain buffer of raw events at the tail and head end of the window. So it kind of looks like this. If you see, the raw values are on the tail and head end, And we pre-aggregate the batch values for the middle windows, middle part of the window, right? Let's say you have a 7-day sliding window here, right? The last day is the streaming update, and the 7th day is the raw value buffer, and we try to aggregate over this thing. The black part is already pre-aggregated, and we focus a lot on aggregation here because it's a form of compressing data. You can't realistically store all the 7 days worth of data in your database. It just blows out really quickly. Right. And as the streaming data comes in, you keep aggregating values for the window. But if you see, you hit a wall there. You can't really move the window past this thing without losing availability or without waiting for the next day's black portion, which is aggregated value. Right. So excuse me for the poor drawing, but we flip the horizontal bar vertically. It's kind of what it looks, or just imagine that this is what it looks like, right? And we want to guarantee availability when we hit that black window without waiting for the next day's batch data, right? So what we ended up doing is basically increase the buffer size a bit more and rely on yesterday's data to compute today's point-in-time correct features. Right. I can take any questions later if you guys have more questions about this. So all of this logic is handled by the client. It handles how the aggregation is done. It handles how to manage availability. You get a client that is written in Java so that it's easy to embed. Side note here, rest of Zipline is written in Scala. Right. And the API is really simple. You give it a list of feature names that you want to pull, and it gives you all the features from different feature sets with point-in-time correctness as Java objects. Right. Next, we want to talk about mutations. Mutations are pretty great to work with if you are a user, but it's really hard to deal with in the system for one specific reason. Mutations mean that you are deleting or updating old data. Right. That is not how warehouses are built. It's all incremental. So how do you delete values from an aggregate? Right. That's a fundamental challenge, but they're easy to deal with. They're almost always consistent with your database, right? When you create mutation streams, right, they have this property that the data is always the same as what you see in the database. If you create an independent stream that is being published by your service, they can go out of sync because there can be retries, or the server can fail and come back, and it can lose data, and the stream can lose data. But if it's mutations, you have 100% guarantee that it's consistent. So this is important not for all models, but for financial models maybe, right? But the thing with mutations is they're not flexible. You cannot enrich it beyond what you have in your database, right? And they're more complex because of the reversibility thing I talked about, right? Let's dive a bit deeper into what I mean by this is more complex because of reversals. A little bit of category theory. I promise it will be really simple. There are these things called monoids. Monoids are nothing but a fancy way of saying we have an associative operator. So plus is associative, which means you can break up the aggregation across different components, and Zipline leverages this very heavily. We break up aggregations across batch, streaming, and the client. Right? All your favorite aggregations like sum, average, and count are examples. Like even computing things like medians are also examples, right? But mutations need a stronger guarantee, which is called a group, which means they're invertible. Things that are not invertible are min, max, median, percentile. So what I essentially mean is that, let's say you have a minimum value that you aggregated across 7 days, and you deleted that, right? What will the new value of the minimum be? You cannot do that efficiently without keeping the entire history of the value with you, right? There are certain compromises that you can make. You can store top K elements and reverse deletions. And for medians, you can use histograms to compute approximate medians. And Zipline offers this compromise, right? So to put it back, we handle deletes as inverses. We just apply inverse of the before, and updates is broken down as inverse of the before and application of the after value. Right. So this is the entire talk. I'll quickly recap what we garbled about here. User gives us a feature set. We create a batch feature set table, which can power the offline training sets. And for online scoring, we need to create feature streams for real-time features, put them together, and offer a client to the user. And we also compute a stats table which powers the data quality UI. So remember the GIF that Andrew showed, that's the data quality UI. We are planning to open source this in next quarter. And this will be a part of the Big Head project. We are talking about Big Head tomorrow. And that's it. Any questions?